And we also saw sample hold circuit
Ah,
and slicing
ah.
and also generation of pulse position modulation wave.
Generation of PPM wave. Just can you tell the block diagram what I have discussed?
Yes, sir.
Ah,
Message signal is given
ah.
as input to sample and hold circuit.
Okay.
The one more
What is
input
the
is
other input to the sample and hold circuit? Is one input is message signal. Another
another
input?
pulse generator.
Yeah, another input is pulses, right? A
Yes,
train
sir.
of pulses we are giving as input. Okay. Then output
The
of the sample and hold circuit is what?
it is U of t. It is
Means
given it is
that is
given to time.
mathematically saying fine, man, but what we say output of the sample and hold circuit.
Uh,
U of t you are writing since I have written in the block diagram. So what will be the output of sample and hold circuit? As
it is
I told about,
PDM,
is it PDM or PAM?
PAM.
PAM, no, because just see, it is just multiplication of message signal and a periodic, a train of periodic pulses, right? So obviously we get a PAM wave. Then output of that will be given as input to the what?
Adder.
Adder circuit, right? So one input is this PAM, another input is the sawtooth waveform, right? So output of that will be given to what?
Threshold detector.
Yeah, threshold detector circuit, right? Yeah. Then output of that will be
It will be given to pulse shaping filter.
pulse shaping filter to get the ppm wave, right? So what will be the threshold detector circuit? Even others can answer, not only Akshay. Others can say what the moment we say threshold detector. Okay. So what would be the circuit? Yes, I'm asking others other than Akshay. Namita or Karanya, even Ramya can answer. Yes, what about Ramya? Threshold detector circuit.
Sir, I couldn't attend classes the
No,
previous
no, that is fine,
week,
whether you
so
were there for previous class or not. But in general, with this fifth semester, right, you are in fifth semester, you might have studied many basics in the lower semesters. Based on that knowledge, I think you will be able to say what circuit you can use to detect the threshold value. See, output of the detector should be what, either 0 or 1. Na? So just can you imagine what would be the circuit you can use and say, yes, I can use this as a threshold detector. Not getting any idea. I heard about comparator. Ramya. Yes.
yes, sir.
Uh, where in which subject you have studied comparator circuits?
DSB, sir.
Where in the DSP?
DSB.
Means what that?
So in third semester, digital system design.
Comparators. Okay. Okay. But here the input is not digital, no? See, PAM after adding, it will be analog. One input will be analog. Right. Another you need to use some reference, right, as a threshold value. So you can use comparator. This op amp as a comparator. Okay. Fine. So I discussed it about the generation and as well as the detection of ppm waves and as well as the noise effects in ppm in the previous class. Okay. So as a activity pod means whatever I discussed in terms of block diagram, it need not be in the same way to generate ppm wave. I think I don't know whether you have studied in previous semester or not. by using 355 timer also, we will be able to generate PWM and as well as PPM waves. You all know how to obtain a stable multivibrator by using 355 timer, right? You're aware or not? One application of 355 timer circuit, a stable multivibrator. Yes, people should say yes or no. Do you know how to use 355 timer as a stable multivibrator? Yes, Skanda. Skanda.
Yes, sir.
Do you know how
Yes,
we
sir.
can
Yes,
use
sir.
355 timer as a stable multivibrator?
Yes, sir.
So with that circuit only, just I will give an idea. When you are connecting 355 timer as an stable multivibrator, you are not going to give any external input, right? And for pin number 5, if you apply a message signal, okay, so pin number 5 is a control signal point, right? If you apply a message signal there, okay, by varying the amplitude of the message signal, you will be able to vary the width of the pulse. Okay, whatever the output of the 355 timer as an unstable multivibrator, now you're getting a square wave, right? With 50% duty cycle, you will be able to achieve on time is equal to off time, right? So if you apply a message signal at pin number 5, and if you vary the amplitude of the message signal, then you will be able to vary the width of the output of 355 timer. Okay, so that will be your PWM output. Then you can give that PWM output as input to the 355 timer circuit, which will be connected in the monostable multivibrator format. Okay, so you all know monostable multivibrator, right? So for pin number 2, you're giving the triggering pulse, right? So instead of giving external triggering pulse, what you need to do is you need to feed this PWM as input to the at pin number 2. Okay, so then you will be able to get a PPM wave. Okay, so I think you can do this PWM and as well as PPM wave generation by using 355 timer. You can use LT Spice as your software tool, and I will give 1 week time. Okay, by next week you should be able to upload in the Google Classroom. Okay, GCR. Okay, this is your second activity. So first, as a part of activity, I have given a few programs, right, to implement in MATLAB on AM and other things, right? AM, SSB and all, right? So this will be your second task activity. Hope got everybody what I said. Using LT Spice tool, okay, make a circuit by using 355 timer to generate PWM and as well as PPM wave. Okay, so with that, let me start my today's task. So we will be discussing today about the quantization. Okay, so far we have discussed about sampling, right? So as we all know, the two fundamental processes involved in the generation of the digital pulse representation of an analog signal is by using sampling and as well as quantization, right? So already first part I said I have discussed about the sampling theorem and its application and all, right? So this sampling process will take care of the discrete time representation of the message signal. Okay, means when I sample an analog signal, it is going to discretize that signal only in time. Okay, but still its amplitude is continuous. Okay, so this quantization process takes care of the discrete amplitude representation of the message signal. Hope this point is clear, I think. I said there are two fundamental processes involved in the generation of digital pulse representation of an analog signal. So what are those two fundamental processes? One is the sampling, second one is the quantization. I said sampling process takes care of the discrete time representation of the message signal. Okay, and the quantization process takes care of the discrete amplitude representation of the message signal. So by combining these two processes, that is the sampling and the quantization, makes the transmission of the message signal in coded form. Okay. Combining the process of sampling and quantization permits the transmission of the message signal in the coded form. Right? Yes, is this fine? I said the two processes, that is the fundamental processes involved in the generation of digital pulse representation of the analog signal are what? Sampling and quantization. I said sampling deals with the what? Discrete time representation of the message signal, and quantization deals with the discrete amplitude representation of the message signal. So by combining these two processes makes us to transmit the message signal in the coded form. Okay. So just as an example, I have taken here, so this is my analog signal. Okay. So when I sample it, it is going to discretize this analog signal in time. Hope I am clear. Yes, students, this is about the sampling. Right. So this is my analog signal. This is a continuous time analog signal. When I sample it at the Nyquist rate, I am going to represent this analog signal in discrete time. Then the second process is what I said, quantization, means it is going to discretize the amplitude of the message signal. Right. So these are the quantization levels, what I can say. Okay. See, I have taken peak to peak amplitude. I have divided that signal into different number of discrete amplitude levels. Hope this point is clear. So discretization of amplitude of the signal is nothing but a quantization. Okay. Discretization or of the signal, analog signal in time is nothing but the sampling process. Yes. How many levels and all we'll discuss. Okay. If I discretize amplitude of the signal in so many levels, what will be the advantage? Okay. If I reduce the number of discrete amplitude levels, what happens? If I increase, what happens? All those things we'll discuss in the subsequent slides. But at least in general, if what you can say is what is sampling, what is quantization, to say in a layman language, if I discretize the analog signal in time, that becomes the sampling. Right? If I discretize the amplitude of the signal, then that becomes the quantization. Okay. I said now, when I do only sampling, the signal will be discrete only in time, not in its amplitude. Still, its amplitude is continuous. Okay, so to make it discrete, the amplitude levels are discrete, so we need to do the quantization process. Okay, so this is one more example, a diagram what I have taken, just for better understanding what I feel. So this is my continuous time signal, wherever I am moving the cursor now. Okay, so this is my continuous time signal. Hope you are able to see my cursor. Then I do the sampling, right? At the sampling interval t, right? This is my t, 2t, 3t, 4t, and so on, right? Okay, so these are my signal samples. Then what is the quantization process? I am going to discretize this my sample signal into different amplitude levels. So I take maximum amplitude as MP and minimum is minus MP. Okay, so these are the quantized samples of this signal. Okay, fine. So any doubts so far? Whatever we have discussed, very basic and very much needed also, and very important concepts also. This has to be there in your mind. Yes, do you have any questions, or shall I proceed further? Hello? Say yes sir, no, at least to say yes sir, no, you don't lose anything, na? Even after showing this diagram and saying what is sampling, what is quantization, you can't say yes or no.
Yes, sir.
Thank you. Let's be responsive, okay? So you can note down these diagrams, because for just to see, you may feel, okay, nothing is there. Okay, when we ask you to again explain, you will not be able to. So that is why just have a screenshot of this, and then it will help you. Anyway, I will share the slides, but as a quick reference, you can have it. Fine. Okay. So let us have in detailed discussion about the quantization process. Uh, okay. So as I said, the continuous signal, it may be voice. Okay. Right. So it has a continuous range of amplitudes, and therefore its samples have a continuous amplitude range. Right. So in other words, what I can say is within a finite amplitude range of the signal, we find an infinite number of amplitude levels. Okay. So what I wanted to say is it is not necessary to transmit the exact amplitudes of all the samples, because we all know any human sense means it may be ear or the eye, right? So will act as an ultimate receiver, can detect only finite intensity differences. See, our ear, our eyes, we can say they're all receivers, right? They're all human sense organs, right? Even skin also, what we can say, right? It can detect only finite intensity differences. Okay. So this means that the original continuous signal may be approximated by a signal constructed of discrete amplitudes selected on a minimum error basis from the available set. Okay. So we can assign the discrete amplitude levels with the sufficiently close spacing. So that is what is shown in the diagram. Okay. So we may make the approximated signal practically indistinguishable from the original continuous signal. Okay. So in the previous class, in the previous diagram slide, what I have shown here, say I'm going to discretize the amplitude of the signal with so many number of discrete levels, right? So with this, I will be able to reconstruct my original signal properly at the receiver side. Okay. So amplitude quantization is defined as the process of transforming the sample amplitude, that is we say m of NTS, right? N into TS it is, okay, of a message signal m of t at a time t is equal to n into TS, right, into a discrete amplitude. So that discrete amplitude we represented by V of NTS. So taken from a finite set of possible amplitudes. So this is the way we define the amplitude quantization. Okay, so it is a process of what? Transforming the sample amplitude. Means m of NTS means what? N can be 1, 2, 3 and so on, right? That is m of TS or m of 2TS or m of 3TS and so on, of a message signal m of t at a time t is equal to n into TS into what? Discrete amplitude. That is V of NTS. So taken from the finite set of possible amplitudes. And here we assume that the quantization process is memoryless. So what do you mean by memoryless? So it won't, its value won't depend on previous or future value. Okay, so that's why it is called memoryless. Okay, and it is instantaneous also. Means the transformation at time t is equal to NTS is not affected by earlier or later samples of the message signal. So that is why it is called memoryless. Okay, and this is one of the simple form of quantization, though it is not optimum, but it is commonly used in the practice. Okay, so discretization of amplitude of a signal. Yeah, this is with respect to block diagram representation of this quantization process. So I give continuous signal, continuous time signal. I represent here for simplicity, I am dropping the time index. Okay, just I'm saying m. I used to write m of NTS now. To make it simple, just I write the input continuous signal sample as just m. Then quantizer. So it does the discretization of the amplitude of the signal. So I represent that as g of some function. Then output of that will be a discrete sample. That is, I used to represent V of NTS. As I said, I am dropping the time index. Just I am representing it by V. Okay. So my input sample is m, and output discrete level. That sample is V. Okay, so the quantizer function is Z. Here I have shown further levels, right? So these are the decision levels or discrete levels, what I can say. MK, okay, MK plus 1, MK plus 2, and so on. Okay, similarly this side MK minus 1 and all. So this is my what in between value is Vk, right? So this Ik is the what I'm going to take the amplitude of that discrete level in this range. Okay. So what I'm saying, when dealing with the memoryless quantizer, I said we are simplifying the notation by dropping the time index, and we use the just symbol m in place of m of NTS, right? And the signal amplitude m is specified by the index k. Okay, that is why it's written here mk plus 1, mk plus 2, and so on. Positive side, and this side it is mk minus 1, mk minus 2, and so on. Okay, so as I said, the signal amplitude m, right, is specified by the index k if it lies inside the interval ik. Okay, this is ik. So the value of ik means when m lies less than mk plus 1 and greater than mk, I represent it by that value of ik. Okay, if the amplitude of the signal, okay, m, right, which is specified by the index k, if it lies inside this interval ik, I have taken some range of ik, right? So I can represent when the value of m is less than mk plus 1 and greater than mk as ik, where the value of k is 1 to L. So I will tell what is this L. L is the number of quantization levels. Okay, L is the total number of amplitude levels used in this quantizer. Yes, is this fine? Okay. Then the amplitudes m suffix k are written, where k is 1 to L, are called the decision levels or the decision thresholds. Fine. So mk, where the value of k can vary from 1 to L. I said L is the number of amplitude levels, right, used in the quantizer. So those amplitude levels are known as the decision levels or the decision thresholds. So at the quantizer output, okay, the index k is transformed into an amplitude Vk, right? So at the output of the quantizer, the quantizer output, the index k is transformed into an amplitude Vk that will represent all amplitudes of the interval Ik. What is Ik? Ik I am representing from mk to mk plus 1. So within this range, okay, if the amplitude, signal amplitude lies within this range, I represented that by the value of Ik. Okay. Okay. So at the quantizer output, I said the index k is transformed into an amplitude Vk that represents all amplitudes of the interval Ik, right? So the amplitudes Vk, where k is 1 to L, are called the representation levels. So hope you are understanding this. Vk is the representation level. I will give an example also. I will show you that example. You will understand better. Okay. It is a generalized representation of quantization process. Okay. Okay. Yeah. The amplitudes Vk are called the what? Representation levels or the reconstruction levels. And the spacing between two adjacent representation levels is known as the quantum or the step size. Okay. Which is actually denoted by delta. I will, yeah. So what I can write is the output of the quantizer, right, which is denoted by V equals Vk if the input signal sample m belongs to the interval Ik. Hope you are understanding. The quantizer output V equals Vk if the input signal sample m belongs to the interval Ik. So the mapping V is equal to G of m I can write. So G of some function was the what? Quantizer function, right? With respect to this block diagram, I can write discrete sample V is equal to what? M in, right? G of m is the input, so G of m will be that one, right? So that is why it is written V is equal to G of m. Is the quantizer characteristics, which is the usually a staircase function by definition. I will show that with example. Okay, before I think I go to the type of quantizers, let me show that representation, then only you'll be able to appreciate this. Yeah, I think so. Yeah, this is also deals with error and all. Okay, fine. I think I don't have that very specific diagram to say. Mm, yeah, I hope you're understanding this diagram. So this with the red color, that is my actual analog signal. Okay, and then the sample signal. Okay, this black color, whatever the staircase waveform is shown, no? That is the 4-bit sample signal, and of course this is the noise. I will come back to this noise. Okay, so here hope you are able to understand. See, 0 to 0.2 is written, right? Between 0 to 0.2, there is a staircase step value, right? That is the value of Vk. Then between 0.2 to 0.4, another step value is there, right? Like that. So within that range, see here, between 0.4 to 0.6, I have this value. That will be the value of Vk, what I wanted to say. It is Mk, then Vk, Mk plus 1 is there, right? So Vk value is what? So if the value of Ik lies within that range, Mk to Mk plus 1, we represent as Vk. Hope got my point. Then between 0.6 to 0.8, yes, this value is there. Okay? Fine. Yeah. So this is what we say. Output of the quantizer is what V is equal to G of M. G of some function is the quantizer, this one. M is my input sequence, right? So we write V is equal to G of M. Fine. As far as quantization is concerned, so there are two types of quantizers we can say. One is uniform quantizer, another one is non-uniform quantizer. Okay. Even in quantizers, we classify quantizers are into two different types. One is uniform quantizer and second one is non-uniform quantizer. So what is uniform quantizer? In case of uniform quantizer, the representation levels are uniformly spaced. Okay? The representation levels means what? That is Vk, right? The value of Vks are uniformly spaced. Then we call it as a uniform quantizer. If they are not uniformly spaced, then it becomes a non-uniform quantizer. That's all. Okay. So, hope this point is clear. Quantizers, as far as quantizers is concerned, there are two types of quantizers. One is uniform quantizer, second one is non-uniform quantizer. So, as I said, in case of uniform quantizer, the representation levels are uniformly spaced. Okay. In case of uniform quantizer, the representation levels are uniformly spaced. And in case of non-uniform quantizer, the representation levels are not uniformly spaced. Okay, so the quantizer characteristics can also be of mid-thread type or mid-rise type. So these are the other two different types of quantizer characteristics. It may be either mid-thread or mid-rise. This comes under within uniform or non-uniform type of quantizer. Okay. The characteristics of the quantizer can also be of mid-thread type or mid-rise type. Right. So in case of mid-thread type, I will come show the diagram and then you will understand. Okay, if I just tell in words, you may not. So this is the mid-thread type of quantization. So x-axis is my input signal, okay, maximum input level, and y-axis is my output level. Okay. So what I'm doing here is I'm going to divide my input signal into different levels. Means I'm going to discretize the amplitude of the signal, right? So these are the decision levels, what I can say, right? So here some value is there, and here, right? So maximum peak, what I've taken is -4 to +4, given both x-axis and as well as y-axis, right? So I'm going to discretize this signal into different discrete amplitude levels. So why it is called mid-thread type is here. See, this is what we call as a thread, right? So it is at the middle of this origin, right? That is why it is called a mid-thread type of quantizer. So to say in words, the origin lies in the middle of the tread of the staircase. As I said, this quantization process leads to staircase waveform, right? So the origin lies in the middle of a tread of the staircase, like graph. That is why it's called mid-tread type. In case of mid-rise type, the origin lies in the middle of a rising part of the staircase, like graph. So rising, it will be this one. This is a mid-rise type. So this point is very clear. Right? See, it is at the middle of the rise of this staircase waveform. Where there is what is called mid-rise type of quantizer. Hope this point is clear. What is mid-tread and mid-rise type of quantizer? There are the two different types of quantizer characteristics, what I can say. Yes, I'm asking you people only, is this point clear? Mid-tread type means, see, the tread of this staircase will be at the middle of this origin. Okay, that is why it is called mid-tread type. See, origin lies in the middle of the tread of the staircase. In case of mid-rise type, the origin lies in the middle of the rising part of the staircase. Okay. So here the tread lies in the middle of the origin, right? The origin lies in the middle of the tread of the staircase waveform. Here the origin lies in the middle of the rising of the staircase waveform, right? So this is the mid-rise type of quantizer. So as I said, these are the decision levels. It may be say 1 volt, and 2 volt, 3 volt, 4 volt, like that. So in between values are not shown, you can write it. Okay, similarly said -1, -2, -3, and -4. Okay. Yes, hope understanding what I'm saying.
Yes, sir.
So this is about the mid-rise, and previous one what I've shown is mid-tread type. So here in this case, we can write this as 1, 2, then 3, 4. Similarly, vertically -1, -2, -3, -4. I will quickly show some more better understanding about this mid-tread and mid-rise. I think with respect to this also, you will be able to understand. Just let me see. Yeah, just think it is about a mid-thread. Okay, so these are the, what I said, input signal, x-axis input and y-axis output, right? So these are the decision levels. D1, maybe notations are different because since I have taken from different source. Okay, there I have not written anything, D1, D2, D3 and all. You just have written 2, right, 4 and all. So these are the decision levels in the mid-thread type. Okay. X-axis, these are the decision levels as far as the input levels are concerned. And R1, R2, R3, these are what? Reconstruction levels for the output. Hope you are getting my point.
Yes, sir.
So just have a look. So it's a function of, see, from this point, and this we say dead zone from -D1 to D1 is a dead zone. This output will be 0 during this time. Okay, for the input from -D1 to D1, right? Okay, so I will go back to that. Yeah. Here also I have taken another example. So both this is mid-rise type and this is a mid-tread type. How it will be divided? So this is the peak-to-peak range from year to year. Okay, which is not clearly visible. You can. I'm just reading it down and saying. So this is peak-to-peak range. So I've taken here delta, 2 delta, 3 delta, and so on. Similarly, down delta, -2 delta, -3 delta, and -4 delta. Okay, just see here the x-axis. It is divided delta by 2, 3 delta by 2, right? There are 5 delta by 2 and so on, 7 delta by 2. Similarly, the negative axis. Should be able to understand the difference between mid-tread type and mid-rise type. In case of mid-rise type, see x-axis will be what? Delta, 2 delta, 3 delta, 4 delta, and so on. Okay, similarly the negative axis, and y-axis will be what? Delta by 2, 3 delta by 2, 5 delta by 2, 7 delta by 2, and so on. Similarly for negative axis. Just take a minute, because at one stretch you may not be able to understand. Have a look, try to write down in your notebook and try to understand. Okay, with respect to the previous slide, I said these are the decision levels, right, in case of mid-red type. Hope you are noting these 2 points. This is a good example what I can say. You don't worry about these numbers, I will tell, that binary representation levels. No? I will come back to that. Yes, noted this point. Take 2-3 minutes, just realize how it has done. So I was discussing about these things, mid-red type and as well as mid-rise type. So these are the 2 different types of quantizer characteristics. I said in case of mid-red type, so these are the decision levels, right? So this will be, I said delta is a step size, right? What is step size? It is the difference between the adjacent sample values. Okay, amplitude difference level between the other samples. So this will be delta by 2. Next it will be 3 delta by 2, 5 delta by 2, 7 delta by 2, and so on. Similarly for negative side also. Here this y-axis will be what? Delta, 2 delta, 3 delta, 4 delta. Similarly for negative y-axis you can write minus delta, minus 2 delta, minus 3 delta, minus 4 delta. Okay. But for this one, mid-rise type, x-axis will be what? X-axis will be delta, 2 delta, 3 delta, 4 delta, and so on. Similarly, for negative side, you can write minus delta, minus 2 delta, minus 3 delta, minus 4 delta. Okay, as far as this example is concerned, I can say the value of delta is 1 volt. Okay. So y-axis will be what? That is delta by 2, 3 delta by 2, 5 delta by 2, 7 delta by 2, and so on. Similarly, the negative side. Hope getting my point. I took delta, that is step size, as 1 volt here in this case for whatever the example I have shown. Okay. So these are the 2 important characteristics of the quantizer, mid-red type and mid-rise type. Okay. So you should be able to differentiate between these 2. So where the decision levels are. For mid-red type, decision levels are what? X-axis, right? Yeah. So the use of the quantization, this introduces an error. Okay, defined as the difference between the input signal and the output signal. Because why do we say this quantization process introduces the error is because we are rounding off to the nearest level. Okay, I will go back and sorry. Yeah, with respect to this diagram only I will I think. I have in different slide, I think. So what I am saying is, so this is my input signal. Okay, dotted line is there now. This is my input signal. So when I do the quantization, what happens? I get a staircase waveform, right? Hope understanding what I'm saying with respect to this diagram. So this is of mid-red type, right? Mid-red type. I said the dotted line, this dotted line is my input signal. Okay, that is from peak to peak. This is a peak to peak value. So what I'm doing here is, if I start from here also, it keeps increasing by delta, right? Yes or no? Hope you're getting my point. Even if I start from here, it keeps increasing by delta, right? Then next 2 delta, then 3 delta, and so on. Similarly, this side also delta, then minus 2 delta, minus 3 delta. So here there is a difference between my input signal and as well as my staircase. It is a quantizer signal, right? So that difference is drawn here. Okay. So that is maximum is what? It is plus or minus. It is peak is delta by 2 and this is minus delta by 2, negative peak. So overall, so difference between those two will give you the value of delta. Okay. So here I have taken means this is my with the 3 bits now there are 7 levels. Okay, means 7 means 8 levels. What I can say if I want to say from 1 to this one, okay, 0 to 7 means it is 8 levels, right? So if I take this as 0th level, okay, and this I have taken as 1, then 2, then 3 on negative side, right? Hope you understand. This is my 0th level, then 1. So binary representation 1, right? Then it is 2, then it is 3. So now this side 4, 5, it is 5, okay? It is 5, then 6, then 7. Okay. So this 0th level I can take it as either 0 or 4. This is one way of representing. Other way also I can write. I can start writing from here only 0 to 7. Okay, there are different ways to write and represent this amplitude level. So don't have to worry about that. Just now what you need to understand is, so when I do the quantization, okay, so it introduces some error. That error is known as the quantization error. What that error is, there is a difference between the input signal and the quantized signal. That is known as the quantization error. Hope got this my point. I don't know to what extent people are understanding this waveform. This is the quantization error, what I can say. Yes, able to understand with the dotted, this one is written and how does it oscillates between plus delta by 2 and minus delta by 2? Because from year to year it is delta, right? This value will be delta by 2. Yes or no?
Yes, sir.
Wherever cursor I have kept, no, that value is delta by 2. Yeah. Because this is an important concept. Yeah. One more diagram I was shown between input signal and output signal, right? And then how do I get this quantization error signal? So this is what I wanted to say error. Plus delta by 2 to minus delta by 2, and that keeps repeating, okay, at each decision levels. This is at one decision level, right? This is the next decision level, and so on. Yeah, this is what I was talking about that. So use of quantization introduces an error defined as what? A difference between the input signal M and the output signal V. So that error is known as the quantization noise. So this is one of the important what I can say the concept in the quantization process. Okay, when I do the quantization, I said it introduces error. How do I define that error? It is the difference between input signal and the output signal. Okay, so in the next diagram is not the next slide. Next to next slide, I have shown this variation of quantization noise as function of time by assuming the mid-red type. Okay, this is a different slide what I have shown here for better understanding. So this diagram is about that. Means this is my input signal, okay, the dashed one, and this staircase waveform is my quantizer signal, and I think here it is shown, right, the difference between input and the output, that will be an error, okay, and that keeps repeating, right, and here it is taken at peak, positive peak and negative peak, it is shown like this, okay, rest of the things it is oscillating between plus delta by 2 and minus delta by 2. Hope this point is clear. So the dashed line is my analog signal. The staircase waveform is my quantizer version of the signal. So I'm taking the difference between the input signal and the quantizer signal. That difference will be the quantization error. Right? Because it is off of, means if I take step size as delta, it will be off of that. Right? Hope we're understanding this point, from this point to this point. So it is delta by 2. Either it may be plus delta by 2 or minus delta by 2. So that is the maximum error it can occur in this quantization process. Who got my point? The maximum quantization noise or error can occur during the process of quantization is either plus or minus delta by 2. Okay, whatever here it is shown for plus delta by 2, similarly the next part will be the minus delta by 2. Yes, understood this point, my dear students?
Yes, sir.
Why I am stressing on this is many will not be able to catch this point. That is why I am stressing on this. How this delta by 2, okay, even that mid-red and mid-rise type also, I don't know to what extent how many could get that point. The decision levels, what I said, delta, 2 delta, 3 delta, and so on. Then for other case, it is delta by 2, 3 delta by 2, 5 delta by 2, 7 delta by 2, and all. Okay. So please have a look, think by yourself, and then if you have any difficulty, you can approach me. Okay. Yeah, this is the diagram. What actually from your textbook to understand the quantization error. Okay. I said it will be plus or minus delta by 2. Just for better understanding with colors, I have given this. Of course, that error signal is also drawn at with the origin. Okay. In the previous diagram, it is shown it separately. Sorry. So I thought with color people will get attracted. So that is why I kept that slide also. Fine. So wherever there is a color, people attraction will be more. So here that is why shown with actual signal by red color, then sampled version, that is quantizer signal with black color, then the noise by the what color it is? Green color, right? Yeah, this value will be plus or minus delta by 2. Okay, that's one more I thought can be told in this way also. Kept this slide also. Is this fine? Shall I go ahead? This 5 minutes is left out. I don't know, I will not be able to complete this. At least I can tell this much. Yeah. Yeah, if I consider the quantizer input as M, right, that is my continuous time signal, the sample value of a zero mean random variable M, I denote it here. So if the input has a non-zero mean, we can always remove it by subtracting the mean from the input and then adding it back after quantization. Okay, just it is for mathematical representation of this quantization error. We are dealing with that. Okay, I represent the quantizer input as what? M, right? The sample value of that having a zero mean and random variable I used to represent by capital M. So small m is the sample value, capital M is the random variable. I hope by this time you are able to understand, make the difference between small variable and capital variable. So we used to represent the random variables by capital letters and its sample value by small letters, right? Okay, so the quantizer means what? G of some function, right? That is G of M. Maps the input random variable M of the continuous amplitude into discrete random variable V, right? So their respective sample values, I can write it as small m and V, right? So those two are related by what? Usually I wrote V is equal to G of M. That is what the equation 1 was, right? So now the quantization error, which will be denoted by the random variable, what? Capital Q, and its sample value by small q. So hope understand this, what I say. The quantization error will be denoted by the random variable, capital random variable Q, and its sample value by small q. Then we can write small q, that is its sample value is equal to M minus V, where M is the sample value of the input signal to the quantizer and V is the sample value of the output of the quantizer, right? Either in terms of sample value or in terms of random variable I can write. So this is in terms of random variable, that is capital Q is equal to capital M minus capital V, right? So this is my random variable for the quantizer, right? Quantization error, capital Q, and M is the what? a random variable for my input signal, and V is the random variable for my output of the quantizer. So with input M having zero mean, right, and the quantizer is assumed to be symmetric. So what we can say is the quantizer output V and the quantization error Q will also have a zero mean, because my input signal is having a zero mean. That is why I am assuming that the quantizer output and quantization error is also have a zero mean. So for partial statistical characterization of the quantizer in terms of output signal to noise ratio, so we need to find out only the mean square value of the quantization error Q. Okay, so we need to find out the mean square value of the quantization error Q. So let us see how to find that mean square error. Okay, so to do that, so I think with this I will stop. Okay, so because it will not be able to complete. There are the derivations which we need to understand about this quantization error. We need to find output SNR and all. So okay, let me stop with this. Okay, so if you have any questions, you can ask, because I will not be able to complete in another 2 minutes. That is why I am stopping.